Welcome to my mathematics channel. I'm your host, Ted Z. Behold this awesome infinite product that works out to 2 over pi. This fantastical creature is called Vieta's product. Vieta was actually French. His real name was François Vieta with an accent grave on the E here. But I suppose we like to use his Latinized name, Vieta. So let's have a look at this thing. This is a bunch of factors that go on forever. So the factor, the first one is 1 over root 2, and they get bigger and bigger and bigger. Okay, and if we keep multiplying them together, we're approaching 2 over pi. Now, the first time I saw this, I was very young, and I was completely mystified and dumbfounded by this. I thought, why would all these roots of 2 work out to 2 over pi? I also felt that I would never understand something like this because in those days, I didn't really know much, right? But actually, it's not that hard to understand, and you will understand by the end of this video. Okay, first I want to see this in action. I want to see if this actually works. So we'll call this V1. It's just one term. And if we take the first 2 terms, we'll call that V2. And if we take the first 3, not terms, but factors, if we take the first 3 factors, we'll call that V3. And we can compile this into a table and see how well it approximates 2 over pi. So Vn is going to go to 2 over pi, but 2 over Vn, this should go to pi. So I'll put both of these in a column, in their own columns in a table. There we go. So this number here is 2 over pi, and this, of course, is pi. And as you see, Vn after 15 factors really does come close to 2 over pi, and it does come close to pi over here. And you see the error is small. Maybe it's not as fast as some other ways we have of calculating pi, but it's still pretty good. All right, the question is now, why does this fantastical, unimaginable formula work? Well, to answer that question, we need to do some proofs. Start by proving Euler's sinc identity. Sinc is not the thing in your kitchen, it's the function sine x over x, which appears often in analysis. Here's the double angle identity. Everyone knows this. And we can divide the argument by 2. And now we can use a really beautiful idea. If you notice here, we have sine x over 2. So we have sine of something. Well, I can apply this formula again to try to eliminate this sine. I'll get another sine, but I'll get another cosine. You see? So let's keep applying this formula over and over again. So let's see what happens here. So I'm going to try to substitute something for sine x over 2. So I use this formula again, and I get 2 sine x over 4 cos x over 4. Great. But I want to eliminate this now. I'll try at least to eliminate this. Okay, so I'll use this formula again. And I have sine x over 4 is 2 sine x over 8. Let's write that neatly. Cos x over 8. And I can keep going with this as far as I want. All right, so now let's get a formula for sine of x using this technique. So we'll do it in steps. This is n equals 1. This is the original formula. 2 sine x over 2 cos x over 2. We didn't do any substitution yet. Now n is 2, so we'll do one of these substitutions. We'll do this one. And you'll notice what happened here is that I have introduced another cosine factor. So every time I do a substitution, I end up with one sine, a different sine, and another cosine factor. All right, let's do another step. This is going to be the third substitution, this one here. And I get this. All right, so the pattern is pretty clear. I have here n factors of 2. Here I have 2 to the power n, and this highest denominator in the cosine factors is also 2 power n. So here for n is n, the nth substitution, I get the following. And that's a really beautiful formula, really nice identity. So, of course, the question is now, what happens when n goes to infinity? Well, if you think about this argument here inside the sign, this becomes very small. So x over 2 power n, well, 2 power n becomes really big. So eventually this goes to 0. So it becomes small, I should just say small. And when things are small, when u is small, then sine u is approximately u. And if you want a proof of this, there is a video I did a while back about derivative of tangent. I'll put the link in the description box. And I do a geometrical argument as to why this is true. So as n goes to infinity, sine x over 2 power n goes to x over 2 power n. And so I end up with this canceling out. This here cancels out with this here. And what do I get? I get an x here now, because the limit as x goes to infinity of this is just x. And this now is infinity. And so I bring the x to the other side and I get Euler's sinc identity. Euler's infinite product for the sinc function. Sine x over x. What a beautiful expression. It's an amazing, amazing formula. Now for Vieta's formula. Start with Euler's infinite product for sinc. Here I have unrolled it, and now what I want to do is put x is pi over 2. And as you know, sine pi over 2, sine 90 degrees is 1. So there, our Vieta series is starting to shape up. At least I have a 2 over pi on the left-hand side. And on the right, I have cos pi over 4 times cos pi over 8 times cos pi over 16, and so on and so on. Now, I'm going to use a very interesting trick. I'm going to use this half-angle identity in a very cool way. Now, I've written it in a bit of a funny way with 1/2 plus 1/2. That's because of the way I'm going to use it to make it more clear. So let me rewrite these factors as the following. Cos pi over 4 times cos, this is cos pi over 4 divided by 2. And this is cos pi over 8 divided by 2. So what I'm saying here is that this next factor, this is cos of this angle here divided by 2. So it's the previous angle divided by 2. And here also, this is the previous angle, this whole angle here divided by 2. Pi over 4 divided by 2, that's pi over 8. So if I can figure out the first cosine, I can then get the rest of them by applying this half-angle identity. So as you know, cosine of pi over 4 is root 1/2. Now I plug in the 1/2, root 1/2 in here. Okay, so watch what I'm doing. I have 1/2 of pi over 4, so I'm going to apply this formula here. And I get this 1/2 root 1/2 plus 1/2. Now, cos x, that's the cosine of the previous angle, which is root 1 over 2. Now, that's hard to explain, but I think you can see the pattern here. This is the cosine of the previous angle. This is the new cosine of the new angle here, and this is the previous one. Yeah. Okay, so it's kind of easy now to calculate the next term. I just do 1 over square. Okay, square root 1 over 2 plus 1/2. Now the previous cosine. The previous cosine is this whole thing. All right, so it's this awesome formula is starting to take shape. Okay, it makes sense. It works. All right, so actually, let me do one more term. The next term is 1/2 plus 1/2 times, okay, the cosine of the previous one, that's this whole thing here, this monstrous thing here. Okay, so it's 1/2 plus 1/2 root 1/2 plus 1/2 square root 1/2. That's hard to explain, but once you do it for yourself, it's easy to figure out. Let's see, did I get that right? I hope I got that right. You can check it like this: 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay, that's okay. All right, and so on and so on. So we did it. There's Vieta's formula for 2 over pi. Now, I know what you're thinking. This was Vieta's formula as it appeared on my thumbnail. So is this really the same thing as the formula I just proved? And yes, of course it is. And I want you to prove that. As an exercise, derive this. This is a kind of prettified version of Vieta's formula. I think it's the most common one that we see in books. But I want to give you a hint. Okay, a hint, because I don't want you to go off into the weeds with square root 2. So instead of using this version here of the half angle identity, let's change it around a little bit. What I can do is multiply the top and bottom of the stuff inside the root by 2, and I get 2 over 4 plus 2 over 4 cos x. And now I factor out the root 1 over 4, and I have 1/2 square root 2 plus 2 cos x. Okay, so I think that if you use this version of the half angle identity, it will work. And why don't you try it and let me know in the comments. So like, comment, and subscribe if you really like this video. Send me a super thanks. And I will see you next time with more amazing and cool mathematics.